let's talk about maxima and minima. So to start with, let's look at a couple of definitions. When we talk about maxima and minima, we're really talking about maxima and minima of functions. So let f be a function that's defined over some interval I. And we're going to have c be an element of I. That means at some point inside of I. So we say that really there should be an f there. So let's say we say f and f here. We say f has a absolute maximum on this interval I at the point c if f of c is greater than or equal to f of x for all x in your interval I. Okay, so that's what an absolute maximum means. Now, an absolute minimum, this absolute minimum, that is going to occur when our f of c is less than or equal to f of x for all x in I. Okay? So if we were to take a look at this picture on the right-hand side over here, when we look at this picture, I guess the first thing I would say is that our interval I, in this case, is going to be equal to the closed interval from 1 to 4. Okay? And I hope we can see that we have an absolute maximum. In other words, the biggest y value is 4, and that occurs at the x value of 4. So the point where the absolute maximum occurs is 4, 4. This is the absolute max. And in this case, the role of c is being played by the number 4. So put a c over here. Now that I look back at my definition of absolute minimum, I could see that in this definition, we're putting our minimum at the x value of d. So let me change this c here to a d. Change that to a d. And then what we're going to see is that our absolute minimum in our example occurs at the x value of 2. So the minimum, absolute minimum occurs at 2, and the point associated with that is going to be 2, 0. So that's our absolute min. All right. So it's just an easy visual example of an absolute max and an absolute min. Let's take a look at the extreme value theorem next. So when we use these words, extreme values, when we use those terms, that usually means maxes and mins. So we call maxes and mins extreme values. All right. And this theorem has two conditions. So the first condition is that we need f to be continuous. Well, it's really one condition, I guess. It's continuous on a closed interval AB. So it's one condition because it's one statement, but there's these two ideas. One idea is continuity, and the second idea is that you have to have a closed interval. So when you have both of those conditions occurring, I also want to point out that we use these square brackets here to mean closed interval. So, square bracket means closed, which means you include the endpoints. Okay. So when you have a closed interval, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some point, at some numbers c and d inside this closed interval. So the example we have up above is a great example of this extreme value theorem. But these two pictures we have here are really designed to illustrate the fact that we really need this condition to hold. So let's take a look at this picture on the left over here. When I look at this picture, I can see that this has no absolute min. Okay? If I look at the x value of 2, it looks like it's getting closer and closer to this value of -2, but it never quite reaches there. And I can see that because I have an open circle over here. So you might say, hey, does this violate the extreme value theorem? And the answer to that is no. And the reason why is this function that we've drawn here, it's not continuous. So because it doesn't satisfy the conditions, it doesn't violate the theorem. So we could say, this is not continuous. All right. Let's take a look at this next picture on the right over here. So when I look at this picture, it looks like my function keeps getting bigger and bigger and bigger the closer I get to 2. Okay? So when I look at this guy, this has no absolute max. But this also doesn't violate my extreme value theorem because it doesn't satisfy this condition. In other words, this guy is continuous on the interval 0, not including 2, but it's not continuous on 0, 2, where I include the point 2. And that's because 2 clearly has a vertical asymptote there. So 2 is not even in the domain of this function. All right? So the point of this is we need continuity on a closed interval in order to guarantee an absolute maximum and an absolute minimum. I would like to conclude this video by talking about local maximums and local minimums. So we'll have a local maximum at C, a local minimum. For consistency, why don't I just change that C to a D? Whoops. Let's make that a D like this. Okay. So f has a local maximum at C if f of C is greater than or equal to f of x for all x near C. So it doesn't have to be bigger than f of x for all the things in D. It just has to be bigger near C. And I'll show you a picture in a moment to illustrate the difference. Similarly, a function f has a local minimum at D if f of D is less than or equal to f of x for all x near D. So let me just change that to a D there. So let's draw a quick picture. Okay, my picture will look something like this. And let's have our function start up here. It kind of comes down, comes back up, comes down, and then goes like this. Ends there. All right. So what you can see is that we're going to have an absolute maximum at the value of x equal to 0. We are going to have let's label this point here 1, this point here 2, and this point here 3. Clearly this drawing is not to scale, right? We have an absolute minimum at x equal to 3. But the 2 points that I'm interested in are this point here at x equal to 2. So this point right here, this is going to be a local maximum. So in our particular case, the role of C is being played by 2. And you can see that this guy is the biggest y value near 2. But if you expand the domain, it's not the biggest number on the whole domain. It's only the biggest number near C. Similarly, if I look at the x value of 1, you can see that 1 at x equal to 1, we're going to have a local minimum. So this is a local minimum. And just to reiterate, at this point of 1, It's smaller than anything else near it, but it's not the smallest thing on the whole domain, because at x equal to 3, we get y values that are smaller than the y value at x equal to 1. All right? So this concludes this video on maxima and minima, and we'll talk about critical values next. Take care.